Let's complete the square. A visual representation. Consider completing the square as a puzzle game, where the aim of the game is to form a square with the given shapes. A square tile of length x, giving the area x squared. A rectangular tile of lengths x and 1, giving the area x. A small square tile of length 1, giving the area 1. And also a couplet of 1 and -1, which we call it a zero pair. Let's take a look at the first puzzle. Complete the square with x squared plus 2x plus 1. Now this would mean that the puzzle requires one x squared tile, two x tiles, and one 1 tile. To form a square using these shapes, we align one x tile beside the big square, the other below the big square, and the remaining one to fill the gap in the lower right corner. With this, we form a larger square of sides x plus 1, hence x squared plus 2x plus 1 can be expressed as bracket x plus 1 close bracket squared. Let's try another one. Complete the square with x squared plus 4x plus 4. We'll start by laying out the tiles that's required, and then we will align the x tiles in this manner. The two x tiles to the side and the other two x tiles below. In doing so, we realize we have formed a square gap of 4 square units to be filled up by the remaining 1 tiles. Hence, we have formed a larger square of sides x plus 2. An observation that you should make now is how we split up the x tiles into 2 groups, aligning half of them to the side and the other half below. This is the main part of the trick in completing the square. Concluding this example, x squared plus 4x plus 4 can be expressed as bracket x plus 2 squared. Suppose we only have x squared plus 4x instead. We can align the x tiles using this method earlier, but we will have a missing space that needs to be filled. Here's where the concept of zero pairs come in. We know that we will need 4 1 tiles to fill that space, so we introduce 4 zero pairs into the system and move the 4 1 tiles to fill the space. We have formed our larger square of length x plus 2. However, we will have a balance of -4, but that's okay so long as we are able to form the larger square with the given tools on the left hand side. Algebraically, we now have x squared plus 4x plus 4 minus 4, whereby the first 3 terms as seen forms a complete square, re-expressing the whole expression as bracket x plus 2 squared minus 4. Now that we get the idea of splitting the x tiles into 2 groups, let's take a look at x squared plus 7x. Instead of using 7x tiles, let's now use a rectangular 7x tile with a height x and length 7. As completing the square works when we split the x tiles into 2 groups, we will now cut the 7x tile into 2 equal rectangles of lengths 3.5, with a height remaining as x. Aligning these tiles will be a piece of cake. But here comes the problem. What is the area of this empty space? Remember the dimensions of the 2 rectangles? This will help us in finding the area. With that, we realize that the missing area is 3.5 squared, so we will need to add a zero pair of 3.5 squared. As such, the whole expression below now becomes x squared plus 7x plus 3.5 squared minus 3.5 squared. Moving the 3.5 squared tile into the gap, we now have completed the square of sides x plus 3.5. Back in the algebraic expression, we group the first 3 terms together and the final expression is now bracket x plus 3.5 squared minus 3.5 squared. How about x squared plus 5x minus 2? We'll start by laying out the tiles needed, and as with the earlier example, we will use a rectangular 5x tile of height x and length 5. We then split the 5x tile into 2 equal parts as shown, and align the tiles as how we have been doing all this while. Don't forget the 2 -1 tiles in the process though. Once again, we have a missing area that needs to be filled, in which, after determining the dimensions of both the 2.5x tiles, we figure that the missing area is 2.5 squared. We then add a zero pair of 2.5 squared, hence our algebraic expression is now x squared plus 5x plus 2.5 squared minus 2.5 squared minus 2. We then move 2.5 squared into the gap, forming the larger square of length x plus 2.5. The first three terms in the algebraic expressions completes the square. And what's left outside are minus 2.5 squared minus 2, which we evaluated to be minus 8.25. Therefore, our final expression is now bracket x plus 2.5 squared minus 8.25. To generalize this, if we are to complete the square with x squared plus bx is the same as having an x squared square tile and a rectangular bx tile of height x and length b. The main trick is to halve the length of b so that we have two smaller rectangular tiles of length b over 2, then aligning them next to the x squared tile in this manner. In doing so, we form a missing square area of bracket b over 2 squared, which compels us to introduce its zero pair, b over 2 squared and negative b over 2 squared. The algebraic expression now becomes x squared plus bx plus bracket b over 2 squared minus bracket b over 2 squared. When we move the smaller square into the gap, the larger square of length x plus b over 2 is now formed. Algebraically, it is made up of the first three terms in the expression, hence its final expression, bracket x plus b over 2 close bracket squared minus b over 2 squared. Even if we have x squared plus bx plus c, the most general form ever, we can do the same. Just that we leave the constant term c on the side to be a spectator watching the steps of completing the square taking place. The constant term c only joins back the game after the square has been completed, only to be evaluated together with minus b over 2 squared. To summarize this, x squared plus bx plus c is now re-expressed as bracket x plus b over 2 close bracket squared minus b over 2 squared plus c. And that's the end of the visual representation of completing the square. Be sure to watch parts 2 and 3 when we extend into more conditions in the quadratic expressions. Don't forget to like and subscribe.